Chances are you clicked on this video to know what it is I'm expecting that you know for this series, so that you may start exploring these ideas before coming back, or perhaps you decided you just want to listen and get exposed to the ideas because my introduction video was catchy. In any case, I won't tell you what I expect that you know. Like I do, you know whatever it is you know, so let's just introduce the concepts that we'll be using. We'll just walk through the landscape, not waiting for the neuroscientists to invent walking. We'll stand on the shoulders of giants such as Einstein and tell him what lies ahead in the future, in a world where I get to solve Einstein's equations with code and I don't need to wait until I master covariant derivatives to even start dealing with general relativity. Here goes nothing. Back in the days, a mathematical curiosity came to me which was purely theoretical and wasn't aimed at solving any problem in particular. I just wanted there to be a number outside of the complex plane that extends it, for which its product with its conjugate was negative and yielded -1. I ran through a lot of troubling times, where the set was infinite dimensional and I couldn't do anything with it, and like two rivers merge, as I was learning about special relativity, I finally was able to find the right rules for the set. It ended up being pretty similar to results from geometric algebra and was helpful in computing Lorentz transformations. It had what you could call one complex time dimension and one complex space dimension. When I wanted to have enough dimensions to describe space, I was wondering about adding an extra fifth dimension that can carry a Lorentz-like transformation. This allowed me to algebraically build a complete representation of covariant and contravariant components of a 4-position in my space-time ultra. The ultra here is not me inventing a new video quality name for my dimension, but rather a way to signal two things. That I care about calling things in a way that can outlive me, and to wave my hand to the nerd fighters which listen to Strange Charm by the channel Vlogbrothers, and actually have enough exposure to particle physics so that they can sing along and know what they are saying. So, here are the two representations, from which one can derive the description of the metric. If the inner product of both representations is our space-time interval, interestingly, we have a metric that is different from the Minkowski one, yet we get a Lorentz factor for the space-time interval. To deal with a generic case, we will introduce a metric that accounts for space curvature, which is well documented in the case of the FLRW metric. We also get a formula for the scaling factor using a speed and gamma-like parameters. We might as well make them dependent on time. In my universe, the ultra speed evolves from time 0 to infinity from 0 until 1, the maximum in these coordinates, with a slow exponential. If you're asking why, I might as well tell you I'm making up this universe, so you'll have to take it for granted. It will be a solution to the Einstein field equations and allow me to compute the cosmological parameters and see what my universe would look like, far into the future, as well as in negative time, where interestingly, for some period of time, the scaling factor is imaginary, and we will still be able to discuss what is going on during that time. By now, I think I laid a good hook and will keep the tension up for the next part. Don't be fooled into thinking I want you to stop watching. I'll try keeping things tidy and entertaining at the same time. Next time, we'll derive the Friedmann equations for my universe, and discuss how Hubble's law can be a byproduct of the covariant derivative, given by the gamma matrices obtained from the metric.